Hello and welcome to this CE 108 video. So in this video we are going to briefly review some bending problems, and especially we are going to see how to use a graphical method rather than an analytical method to get the trend of how the internal shear and the internal moment is changing as a function of the position. So the idea of this graphical method is really that if you want to calculate the internal shear and the internal moment as a function of the position within a beam that is subjected to some transverse forces or some distributed loads, this is useful in order to calculate the normal stress and the shear stress that the beam is going to be subjected to. But if what you care is not to have an analytical expression of the internal shear and the internal moment, if all you care is a trend to see at which point within the beam the internal shear is maximum, it means that in this case the shear stress is going to be maximum at this point. Or if what you care is to check at which point is the internal moment maximum, which means that at this point the normal stress will be maximum, then in this case the graphical method is a convenient way to quickly just get the trend, even if you don't get the analytical equation that is governing the evolution of the internal shear and internal moment. Just having the trend allows you to quickly see what is the shape of the curve for the internal shear and internal moment, where is it maximum, so that it will give you the point at which the stress is likely to be maximum, which gives you the most likely point at which the beam is the most likely to break. So let's consider an example to see how this graphical method can be applied and used to quickly identify at which point the internal shear and the internal moment is maximum. So here what we are going to do is to take a given example of a given beam subjected to some given loads. The idea being to take as an example to illustrate what are the different steps that are needed in order to solve this kind of problems. But also to see what is the level of justification that I would expect during an exam to properly justify all the steps and how to graphically integrate the load into the shear and the shear into the moment. Okay, so let's consider the following example. So let's consider a beam that is of length 2L. So the beam is going between x equals 0 to x equal to L, and the beam is attached at x equals 0 to a fixed support, and then this beam is going to be subjected to some loads. So between 0 and L, it's subjected to a distributed load that is going upward like this, and between L and 2L, it's subjected to a distributed load that is going downwards, so like this. We are going to consider that the intensity of the distributed load is the same for both of those distributed loads. It's W naught, but one is going up, one is going down. And so we are going to see what are the different steps that are needed if we want to quickly show the trend of the load of the internal shear and the internal moment. So for this, the step one should be always to draw the free body diagram, which is what we just did. Step two, to identify the unknown. So in this case, we have a fixed support at x equals 0. So fixed support means that we have three unknowns. So we will have a vertical force. Here in this case, it's going to turn out that this vertical force is 0. But we are going to show this in a few seconds. In this case here, we still need to define variables, and I can decide to draw this variable as going up or going down. It doesn't make any difference, but if I draw this variable as going directly in the right direction, then I will eventually find that it will have a positive value. If it turns out that I draw this variables with the wrong direction, then I would eventually find that it has a negative value at the end when I write the condition of equilibrium. So in this case, we are going to say that it's a fixed support. So you have a vertical force that I will here decide to draw as going up. You also have a normal force. This one will also turn out to be 0, but nevertheless, it's a fixed support. So there's three unknowns. And then you have a moment. The fixed support prevents the rotation of the beam, so it's creating a resistant moment, which prevents the beam from rotating about this point A here. So in this case, again, you are free to draw this moment reaction as being clockwise or anti-clockwise. If you have some feelings about how you feel the moment will prevent the rotation of the beam, if you have a feeling about whether the moment will be clockwise or anti-clockwise, then you can directly draw this moment with the right direction. But if you don't have this feeling or this intuition, then you can just define a variable MA that would be clockwise or anti-clockwise. And if you happen to define it with the wrong direction, then you would just find at the end that this variable that you introduced will turn out to be negative. Here in this case, this fixed support is going to prevent the rotation of the beam that would otherwise be induced by the distributed load. So you will have two distributed load, one between 0 and L that is going up. This one is going to result in the formation of a moment that will have a positive projection about A. So this one is creating a moment that is going to make the beam rotate anti-clockwise around the point A, while this moment here between L and 2L is going to push the beam to rotate clockwise about the point A. Here in this case, the moment, the two moments, they are associated with forces that have the same intensity. They are both having an intensity of W naught L. One is going to be a positive moment, one is going to be a negative moment, but the arm of the force are different. In this case, this moment here between L and 2L will have a higher arm of the force, so it will be associated to a moment that is more intense. So this moment is going to be predominant, so otherwise this moment would win and would be more intense than the moment creating by the distributed load between 0 and L. So otherwise, is this if this beam was not attached to a fixed support, it would move clockwise because of this moment between L and 2L that has the higher arm of the force about A. So otherwise, since the fixed support is going to be preventing this this moment, then it's going to oppose the moment created by this distributed load between L and 2L. So this moment in this case is going to be very likely to be anti-clockwise to oppose the clockwise moment resulting from the distributed load between L and 2L. Okay, so that was step 2. Step 1 was just to draw the free body diagram. Step 2 was to identify the unknowns. Step 3 is going to be to now write the condition of equilibria. So we are going to start with this. So in this case, so we can always write the condition of equilibrium along 3 directions. So condition of equilibrium along X, condition of equilibrium along Y, and the fact that the sum of the moment about a given point has to be equal to 0. So let's start with the fact that the sum of the projection of the forces along X has to be 0. In this case, there is only one force along X, which is NA. NA is going towards the negative X, so it has a negative projection along X. So when we write its projection is going to be minus NA, and it's the only one, so this one is 0, so it means that NA is equal to 0. Then we can write that the sum of the projection of the forces along Y is equal to 0. So in this case, the forces that we have will be VA, plus we will have the resultant force associated with the distributed load. So in this case, we have 2 distributed load. One, so those are 2 rectangular distributed load. One is between 0 and L. It's a rectangular distributed load. So the resultant of the force will be applied at the centroid of the load diagram, which in the case of a rectangle will be in the middle, that is to say at L over 2. And the magnitude of the resultant force is equal to the area of the load diagram, which in this case is W naught L. Same thing for the distributed load on the right. It's going to be applied at the middle, which is 3L over 2. This time the resultant force will be going downwards, and its intensity will be the same, that is to say W naught L. So now let's write that the sum of the projection of the forces along the axis y has to be equal to 0. So in this case, we have first VA. VA as a positive projection is going towards the positive y, where y is an axis going up. So VA has a positive projection. Then we have the force corresponding to the distributed load between 0 and L. It also has a positive projection, and its intensity is W naught L. And then we have the force that is associated with the distributed load between L and 2L. This time it's going towards the negative y, so it has a negative projection, so minus W naught L. And the sum of those forces has to be equal to 0. So in this case, in this specific case, which is not a general case, then we find that VA has to be equal to 0. So in this case, the vertical resultant force applied by the fixed support is just 0, and that comes from the fact that those two distributed load between 0 and L and 2L are already mutually compensating each other, so there is no need for the fixed support to prevent the beam from going up or from going down. Finally, we can write that the sum of the moment is equal to 0. In this case, we can choose a given point to write that the sum of the moment about this point is equal to 0. So in this case, for example, we can choose the fact that the sum of the moment about point A is equal to 0. So in this case, so what do we get? First, we get the moment MA that is created by the fixed support. This moment is having a positive projection about the z-axis. Z-axis is an axis that is coming towards you. So it has a positive projection. So MA is its projection. Then VA and NA, first they are equal to 0, but even if they were not equal to 0, they would not have any moment about A because the point A is on their line of action. So the force do not create any moments about points that are on their line of actions. Then we have the moment associated with the distributed load between 0 and L. This is also going to create a positive moment, a moment with a positive projection according to the right thumb rule. So in this case, it's going to be a positive moment. The intensity of the force is W naught L, and we need to multiply by the arm of the force about A. In this case, the arm of the force is L over 2, so we get W naught L squared divided by 2. Then finally, we have the moment associated with the distributed force between L and 2L. So this is going to result in a moment that has a negative projection about A. It's a clockwise moment. The intensity of the force is W naught L. In this time, we need to multiply by the arm of the force, which is 3L over 2. So you end up with a moment that is 3W naught L squared divided by 2. And the sum of the moment of those moments have to be balanced. So the sum has to be equal to 0. So in this case, we find that the moment MA applied by the resultant force is going to be so 3W naught L squared over 2 minus W naught L squared over 2, which is 2W naught L squared over 2, which is just W naught L squared. Okay, and you can check that indeed this thing has the unit of a moment, since it's a distributed force. So W naught has the unit of Newton per meter times L square, which is in meter square. So you end up with something that has the unit of a moment, which is Newton per meter. So that was step 3. We need, in this case, in those kind of bending problem, we always need, despite the fact that we are using a graphical method, we always need to first calculate the equilibrium condition to find the value of the unknowns, which is what is going to give us the limit condition. So let's move this a little bit on the side. So let's go to the next step. So the next step is to check if you have any discontinuity in this problem. In this problem here, there is no concentrated force or no concentrated load that is not at the edges of the beam. You have no concentrated force or no distributed load inside the beam, that is to say at a position that would not be the two extremities of the beam. So in this case, and this is step 4, there is no discontinuity, so we don't have to worry about any discontinuity there's no discontinuity of the internal shear or no discontinuity of the internal load. So then we can move to step 5. Step 5 is about the limit condition. The limit condition is the value of the internal the value of the internal shear and the internal moment at the edges. This comes from the fact that necessarily the internal shear and the internal moment must become equal to the external shear and external moment at the extremities. So this is only valid at the extremities. And this is assuming that the external shear and the external moment are expressed with the right sign convention. As a reminder, in this class, the sign convention that we are using for the internal shear is that it's positive if it's applied on the left and going up, and it has to be going down if it's applied on the right. So this is the positive convention for the internal shear, and for the moment we use the smiling convention. So a positive moment is a moment that would make the beam have a smiley face with a convex shape. So this convention is the one that we are using for the positive moment. So now we can express the limit condition based on the value of the unknowns just by making sure we are using the right sign convention. So in this case, at x equals 0, so first the shear at x equals 0 is going to be equal to the external shear. In this case it is VA, but VA is equal to 0, so the internal shear is also equal to 0 at x equals 0. Then we can express the moment at x equals 0. It's going to be equal to the external moment MA, but in this case MA is expressed with the negative convention. MA is a clockwise moment that is applied on the left. So we were expecting on the left side to have a clockwise moment. So in this case the moment at 0 is minus MA because MA is not expressed with the right sign convention that we were expecting for the internal moment, which means that the moment at 0 is equal to minus W naught L square. Then we have the limit condition on the other side of the beam at x equal to L. So same thing, we want to first see what's the value of the internal shear at x equal to L. In this case, this is a free extremity with no external shear apply at x equal to L. So the external shear is 0, so the internal shear will become 0. And same thing for the moment. The moment at x equal to L, this is again a free extremity, so there is no external moment being applied. So the internal moment is going to be 0 on the right extremity. So now that we have the discontinuity or the absence of discontinuity in this case and the limit condition, then we are ready to start plotting the value of the load diagram of the internal shear and of the internal moment, and by to derive each of those curves by doing a numerical integration, graphical integration. So as a reminder here, the main difficulty is to properly justify all the steps that you are doing and to be careful at making the right conclusion. The idea is based on the fact that the internal shear is the load is the distributed load is the derivative of the shear, and the shear is the derivative of the moment with respect to x, which means that you can go from the load to the shear by doing an integration, in this case a graphical integration, and then you can go from the shear to the moment by doing an integration, again in this case a graphical integration. So in this case it's always useful to plot the load diagram, the shear diagram, and the moment diagram on top of each other, which make it clearer on how you graphically integrate the load to get the shear and the shear to get the moment. So in this case, so that would be step 6. So step 6, the first thing is going to be to plot the load diagram. So in this case, we are going to plot the distributed load as a function of x, and we are going to plot it as a function of the position within the beam. So the beam goes between 0 to 2L, and the distributed load is going to change at x equal L. So in this case, be sure you remember what's the positive convention that we are using in this class. In this case, the positive convention is that the distributed load is positive if it's going upwards. So in this case, you have a constant distributed load. It's initially positive between 0 and L because it is going upwards. So it's equal to plus W naught. And then after that, it's still constant. It's a homogeneous distributed load. Its intensity is still W naught, but this time it becomes negative because it is going downwards, which is the negative sign convention. So it switches to minus W naught. Then, based on this, the idea of the following step now will be to to graphically integrate this distributed load to convert it into the shear diagram. So in this case, there is several information that you can use to infer what is the shape of the internal shear. So in this case, the goal will be to plot the internal shear between x equals 0 to x equal 2L. And so there's several things that we can use here. The first step in this case will be to place the limit condition. So we have derived a certain number of limit conditions. So we know that the internal shear has to be 0 at x equals 0 and has to be 0 at x equal to L. So that should be the first thing we can say, that at x equals 0, the internal shear has to be equal to 0, and the internal shear also has to go back to 0 at x equal to L. This is due to the limit condition. Then the second information that we can use is what is the type of function that we are trying to integrate. Here we are trying to integrate the load diagram. The load diagram is, in this case, a function that is constant by pieces. So it's constant between 0 to L, which means that when we are going to integrate this constant function, we are going to get a linear function. Same thing between L and 2L, it's also going to be a constant function. Once integrated, it's also going to become a linear function. And then the second thing we can use, now that we know the type of function that we will get for the internal shear, is the sign of the function that we are trying to integrate. Here in this case, we are integrating W. W is positive between 0 and L. So you take the integral of a positive value. It means that the integral will be increasing as a function of x. And then between L and 2L, you have a negative value for the function. So it means that the integral will be decreasing as a function of x. Okay, and in this case, that's all the information we need. We have a function. We know it's a function that is linear by piece. It's initially starting at x equals 0. Then it's increasing linearly with a constant slope since it's a linear function. And at this point, it starts to decrease and go back to 0 at x equal to L. And we know that necessarily the slope at which it increases between 0 and L has to be the same as the slope according to which it's decreasing between L and 2L, because the slope is given by W, and W has the same value between 0 and L and N and 2L, just with a different sign. So then the next step, now that we have the distributed load and that we have integrated that into the internal shear, the last step will be now to integrate this graphically in order to get the internal moment. So same thing, we want to plot the internal moment between 0 to 2L, and same thing, we are going to start first by placing the limit condition. So the first thing that we know is that the moment has to be equal to minus WL2 at x equals 0. So that's the first point that we know. Then we know that the moment has to be equal to 0 at x equal to L. That's the second limit condition that we know. Here we have a few more information that we can use. We know that the function that we are integrating, the shear, is equal to 0 at x equals 0. So if you are integrating a function that is equal to 0, so v is the derivative of m is the integral of v, so v is the derivative of m. So it means that the derivative of v is equal to 0 at x equals 0. So if you have a function that has a derivative equal to 0, it means that this function will have a horizontal asymptote. It's going to be a minimum or a maximum. So in this case, we know that the function will have a horizontal asymptote at x equals 0. And we also have a 0 at x equal to L. So same thing, we know that the function m will have a horizontal asymptote at x equal to L. Then you have a function, we can look at what type of function are we going to get. So now this time v is linear. So when we integrate something linear, we are going to get something that is quadratic. So we will have a quadratic function between L and 2L. And same thing, we are going to get a quadratic function between between 0 and L and between L and 2L. The last thing we can use is the sign of the shear. It's going to give us the evolution of m. In this case, the shear is always positive. The internal shear is always positive, which means that m will always be a function that is increasing with increasing x. So now we have everything we need. We know that m is a quadratic function. We know that it starts with a horizontal asymptote. Then as it gets started, we see that v is increasing, which means that the slope of m starts to increase. At this point, at x equal L, the slope does not increase anymore and start to decrease. So m will continue to increase, but with a slope that is decreasing, and will finish by having a horizontal asymptote at x equal to L. So now, based on this, we have the overall trend for the moment and the internal shear. And the main idea about this is that it's a pretty convenient tool because it allows us to quickly see that in this case, the internal shear is maximum at x equal L, which means that in this case, if the internal shear is maximum at x equal L, it means that the shear stress within the beam is also going to be maximum at x equal L. And on the other hand, we see that the internal moment is maximum at x equals 0, which means that the normal stress within the beam will be maximum at x equals 0. So this is a convenient tool to quickly see at which point the internal shear and the internal moment is going to be maximum, which tells us where the stress is going to be maximum, which in turn tells us where the beam is the most likely to break. Again, if you want to, if your goal is not to get just a graphical trend for the internal shear and the internal moment, then you will need to numerically calculate the internal shear and internal moment. And in this case, you can use different methods. You can use the method of section to calculate the internal shear and internal moment, or to also use the integration method, but this time do a numerical integration method by numerically integrating or analytically integrating W to get V and analytically integrating V to get M. Okay, so let's see another example to make sure we all understand. So let's consider another beam. So this time the beam is still of length 2L, but this time we are going to describe the axis X as going between minus L to plus L, and it's going to be equal to 0 in the middle. This beam is attached to a pin at x equals 0 and a roller at x equal L. Sorry, the pin is at x equal minus L and the roller is at x equal plus L. And this beam is going to be subjected to a distributed load that has a triangular shape like this. So initially, the distributed load is increasing like this. It's going downwards, and then it starts, its intensity starts to decrease again. So you have a distributed load like this that goes between minus L to plus L with a triangular shape like this. Okay, so that was step 1. So this is the free body diagram. So next we are going to identify the unknowns. So in this case you have a pin. The pin at the point A can have potentially two unknowns, a vertical force and a longitudinal force NA. This force NA will turn out to be 0 in this case. And then you have another unknown forces at the point B, which in this case you only have a vertical force because the roller doesn't prevent the motion of the beam left and right, so it only prevents the beam from going up or down. So you only have a unknown force that is going up, a vertical unknown force. So that was step 2, which is to identify the unknowns. So now we move to step 3. So we are going to write the condition of equilibrium. This beam has to be at equilibrium. So let's start with the fact that the sum of the forces along x is equal to 0. So in this case, we have VA and VB, which will have a positive projection. We have only NA on the x-axis. So in this case, we just find that NA is equal to 0. This is on the x-axis. For the y-axis, so y is an axis, vertical axis going up. So the sum of the forces along y equals 0. So in this case, we will have VA and VB that will have a positive projection. Those are the unknown force that we are trying to find. And then you will have, there's different way to solve this, but in this case, you have two triangular distributed loads. So the resultant force associated to those two triangular loads is going to be at the centroid of the load diagram, which is at 1/3. So in this case, this load diagram will be associated with a resultant force that is going to be applied at minus L/3. And this load diagram will be associated to a resultant force that is going to be applied at L/3. The intensity in this case, so it's a triangular load, so its intensity is the area of the load diagram, which is half of a rectangle. So in this case, the intensity would be W0L/2, which is half of the area that a rectangle W0L would have. So in this case, so now we can write that the sum of the forces along y is equal to 0. So we have VA and VB that have a positive force that are going to be counterbalancing those two forces going down. So you will have a W0L/2 plus W0L/2. They have a negative projection, so they are going to counterbalancing VA and VB. So VA plus VB in this case is their sum is going to be equal to W0L. So in this case, we still have a free equation, but only so we have three unknowns, but only two equations. So we cannot directly solve VA and VB, but it's nevertheless a statically determinate problem. In this case, we just need to write that the sum of the moment is equal to 0. So for example, we can take a point C here in the middle. We can say that the sum of the moment about C is equal to 0. So in this case, we would quickly find that it tells us that VA is equal to VB, which we could have guessed by the fact that this problem is symmetric with respect to x equals 0. In this case, VA is creating a moment that is clockwise, that is to say a moment that has a negative projection along the z-axis. So we have minus VA times the arm of the force, which is L. Then we have VB, which is resulting in a positive moment, a moment that has a positive projection along the axis x, and the arm of the force is L. Then we have the moment associated with the load diagram that goes between minus L and 0. This one is resulting into a moment that has a positive projection. So the intensity of the force is W0L/2 multiplied by the arm of the force. The arm of the force is L/3, so the moment is going to be W0L/2 divided by 6. And then finally, we have the moment created by the distributed load that goes between 0 and L. This one will have a moment that has a negative projection. It's going to be a clockwise moment. The intensity of the force is also W0L/2 multiplied by the arm of the force, which is L/3. So you find the moment is W0L² /6. And those sum of moments has to be equal to 0. So in this case, we quickly find that since those two moments counterbalance each other, it has to be that VA is equal to VB. So in this case, we find that VA is equal to VB, and since VA and VB is equal to W naught L over 2, and since they are equal to each other, it means that they are both equals to W naught L over 2. Okay, so now we have the value of the unknowns. So in this case, there is also no discontinuity in this problem. So there is no forces, no concentrated forces that are applied in the middle of the beam. Remember that those forces, those resultant forces, W naught L over 2, those are not real concentrated forces. Those are just the resultant force associated with the distributed load. So those are not real concentrated forces that are applied inside the beam. So here inside the beam, there is no concentrated shear, no concentrated moments. So there will be no discontinuity in the internal shear, no discontinuity in the internal moment. Step 5, we need the limit condition. So we need to know what happens at x equal minus L and what happens at x equal plus L. In this case, so the internal shear and the internal moment will become equal to the external shear and external moment, provided that they are expressed with the right sign convention. As a reminder, we expect that the internal shear should go up on the left, go down on the right, and the internal moment should be clockwise on the left and anti-clockwise on the right. So in this case, at x equal minus L, so the internal shear at x equal minus L is going to be equal to the external shear VA. In this case, VA is already expressed with the right sign convention. It's going up, so the internal shear at minus L is equal to VA. It's W naught L over 2. And then the moment at minus L, in this case, is just equal to 0 because you have no external moment. You have only a pin at x equal minus L, but the pin doesn't prevent the beam from rotating around the point A, so there is no moment that is applied by the pin. So the internal moment would be 0. Then we move to x equal plus L. So same thing, the internal shear at x equal plus L is going to be equal to the external shear VB, but in this case VB is not expressed with the right sign convention that we expect. VB is going up. We were expecting a shear, an external shear going down to be in agreement with our sign convention. So in this case, V at plus L is going to be equal to minus VB, that is to say minus W naught L over 2. And the moment at L equal minus L, same thing. Here there is no external moment at x equal plus L. It's only a roller. The roller doesn't prevent the rotation of the beam. So the internal moment is going to be equal to 0. So based on this, we have everything we need to start plotting the load diagram, the internal shear, and the internal moment. So let's move this a little bit. So let's start first. So let's start with plotting the distributed load. So in this case, we are going to plot the distributed load W between x equal minus L to x equal plus L, and the distributed load is going to change at x equals 0. In this case, the distributed load is always going downwards, and by convention in this class, the sign convention that we use is that a distributed load going downwards is a negative distributed load. So in this case, it's a linear distributed load, so it's initially 0 at x equal minus L, then it decreases linearly up to x equals 0, where at this point it starts to increase linearly. Okay, so remember that in this case, the reason that the distributed load is negative, it's because it's going down, which by convention is associated to a negative distributed load. Then we are going to integrate this graphically to get the internal shear. So the internal shear as a function of x between plus L to minus L. So in this case, so let's start with what we know, which the first thing that we should always put are the limit condition. So in this case, we know that at x equal minus L, the internal shear will be equal to W naught L over 2. And same thing at x equal plus L, the internal shear will become negative and will become equal to minus W naught L over 2. The other thing that we know is that now we can look at what we know about W, and based on this infer some information about the shape of V. We know that W is 0 at x equal minus L, which means that V will have a horizontal asymptote. We know that at x equal plus L, W is also 0, which means that V will also have a horizontal asymptote at x equal plus L. We know that W is a linear function, which means that when you integrate it, you will get a quadratic function between minus L and 0. Between 0 and plus L, it's also going to be a linear function that is also going to become a quadratic function when you integrate it between 0 and plus L. And the last thing we know is that the distributed load is always negative, which means that the quadratic function that we will get by integration will always be decreasing. So based on this, we have all the information to plot the shape of the internal shear. The internal shear starts at x equals 0 with a horizontal asymptote. Then the slope of the internal shear starts to decrease more and more. The slope is W, so W decreases more and more, so the internal shear decreases more and more. At x equals 0, you have an inflection point. The slope starts to re-increase again. So the quadratic function is now becoming convex and will end up with a horizontal asymptote at x equal L. So this gives us the shape of the internal load V of x. Now we move to the last step, which was not to integrate this to get the internal moment. So same thing, we're going to plot the internal moment as a function of x between plus L to minus L. So what is the information that we know in this case? So let's start with the limit condition. We know that the internal moment is going to be equal to 0 at minus L and at plus L. We know that we have a 0 here. V is becoming 0 at x equals 0. It means that the internal load will have a horizontal asymptote at x equals 0. Then we know that we are integrating a quadratic function, so we are going to get now a cubic function between minus L and 0, and same thing between 0 and plus L. We are integrating a quadratic function, so we are going to get a cubic function, a degree 3 polynomial. We know that between 0 and L, the internal shear is positive, which means that the cubic function that we are integrating will be initially increasing, and then the internal shear becomes negative, which means that the moment will be now decreasing. So then we have everything that we need. So it's a cubic function. It's initially starting with a high slope because V is maximum. Then the slope starts to decrease. Then the slope eventually become 0. So the function m has a horizontal asymptote at x equal L. And eventually the slopes become more and more negative. So the function m starts to decrease and eventually become equal to 0 again at x equal L. So again, this allows us to quickly see that in this case, the internal shear would be maximum at x equals minus L and x equal plus L, which means that in this case, at those locations, the shear stress will be maximum at those two locations, x equal minus L and x equal plus L. And that in this case, the internal moment is maximum at x equals 0, which means that the normal stress is going to be maximum at x equals 0.